Here we're asked to use mathematical induction to prove this statement. So we start, as always, with step 1, which is when n is equal to, in this case, 1, because we're starting at r equals 1. Step 1, we have to prove the left-hand side is equal to the right-hand side when n is equal to 1. So for the left-hand side, we have the sum from r equals 1 up to 1 of r, which is just equal to 1. The right-hand side is equal to, when n is equal to 1, 1 times 1 plus 1 over 2, which is 1 times 2 divided by 2, which is 1. Therefore, the base case holds when n is equal to 1. Step 2. Step 2 is when n is equal to k. We're going to assume that from r equals 1 up to k of r is equal to k times k plus 1 divided by bit of a moving around there, k times k plus 1 over 2. There we go. And that's our assumption. Now we move on to step 3. Step 3, which is when n is equal to k plus 1. First of all, what do we want to show? We want to show that the sum from r equals 1 up to k plus 1 of r is equal to k plus 1 times k plus 1 plus 1, which is k plus 2, over 2. Starting with the left-hand side, this is equal to the sum of r equals 1 up to k of r, the sum of the first k terms, plus the k plus 1 term of this. When r is equal to k plus 1, this is just k plus 1. But now we're going to make our substitution because we know that this is equal to this. So we get k times k plus 1 over 2, and then plus k plus 1. We could expand this. I'm just going to factorize out. I'm going to factorize out k plus 1 over 2, which leaves, what do I need to multiply k plus 1 over 2 by to get this? K. And what do I need to multiply k plus 1 over 2 by to get this? Well, I need to multiply it by 2, because I have a full k plus 1 here and half a k plus 1 here. But this is the same as that one, if I rewrite it as k plus 1 times k plus 2 over 2. So that is equal to the right-hand side. So I have shown what I wanted to show, which is that this is equal to this. Finally, we must always remember our conclusion in a proof by induction. And the proof of conclusion states that, hence, by mathematical induction, since the statement holds for n equals 1, and if it holds for n equals k, it also holds for n equals k plus 1, it must be true for all positive integers.